Hello, ladies and gentlemen of geometry. This is your last mathematical logic video, so last section that we're talking about. And here we kind of build on the four statements that we've had before. The conditional, the biconditional, or the conditional, the inverse, the converse, and the contrapositive. So now we kind of look at, we kind of focus on the conditional and the converse, and we kind of see, if they're true or not. So before we didn't really care if they were true. Now we're trying to see, are they true both forwards and backwards? Does that make them a definition? So biconditional is kind of exactly what it sounds like. It's going to be a conditional, but it's going to be a conditional that works both ways. So before we go any further, I'd like to just do a quick review of everything that we've talked about so far. So conditional just means if something, then something else. So if I look over here at the example, if a number can be divided by 2, then it is an even number. Okay, so a number can be divided by 2, that would be that P part. Then it is an even number, that would be the Q part. Converse means switch that around. If Q, then P. So if a number is even, then it can be divided by 2. Inverse means negating the original conditional statement. So inverse, you're kind of taking this original statement and you're using not, okay, or this little symbol tilde means not. So if a number cannot be divided by 2, then it is not an even number. Notice it's in the same order as the conditional, but I'm just using not. Contrapositive means do both of these in one statement. Do the converse and the inverse in both statements. So if a number is not even, then it cannot be divided by 2. So contrapositive means use not and then switch them as well. So those are the four statements. So for any given general statement, you should be able to make 4 statements out of there. If something, then something else. Switch it. Not. If not, then not. So those are kind of your 4. So now we kind of look at, are they both true statements? So if I look at my conditional and my converse, in this case, if a number can be divided by 2, then it is an even number. If a number is even, then it can be divided by 2. That is true. That is also true. So this is called true forwards, which is my conditional, and true backwards, which is my converse. All right, so this is my conditional, this is my converse. If it's true forwards and backwards like this, we can call that a definition, and we can use a biconditional. So here is what we just had. So as a biconditional and as a definition, it would be using a biconditional. So here's what it would be. So a number can be divided by 2, so my hypothesis, if and only if, shorthand would be this, it is even. So that would be the Q. Okay, so in general form, kind of a big idea, using my phrase if and only if implies that it goes forwards and backwards, and that is true both ways. P and Q are my hypothesis and my conclusion. You should be familiar with that. And in mathematics, this is kind of often how we write definitions. So if I take a look, a definition, a number can be divided by 2 if and only if it is even. That is a statement that is true both forwards and backwards. So therefore, you can make it a definition using a biconditional. Biconditional means if and only if. Definition means both statements are true. Both the converse and the conditional are true. Okay, so biconditionals are a little bit different than definitions. You use a biconditional to make a definition, but a biconditional doesn't necessarily have to be true both ways. So let's take a look. So what if one of the ways is false or both of the ways is false? Then if that's the case, I want to use what's called a counterexample. A counterexample does this. It is a situation where the hypothesis is true, but the conclusion is false. All right, so if I say if P, then Q, a counterexample says, well, P is still true, but I made Q false. So if I look here, this example, if the sun is out, then it is warm. So my conditional is P, my hypothesis is Q, and those are just letters representing that. The sun is out, then it is warm. Well, counterexample would be, pick a day in January when the sun is out, but it is like 3 degrees outside and it is really, really cold. And, you go outside and you build a snowman complete with a top hat and a nose. That still would be a counterexample. Sorry, got a little off track there. So it's really cold outside in January, but the sun is still out, so that means it is not warm. So if I look at a counterexample, two angles are supplementary. Remember, that means adds up to 180. Then they form a linear pair. So now remember, a linear pair means this. So a linear pair means two angles together. So angle 1 and angle 2, together they make a line. So they would be considered a linear pair. Now, a counterexample would just be two angles that are still supplementary, but they are not a linear pair. So my counterexample would be something like this. If I have a 130-degree angle here, then I have a 50-degree angle down here. Are these two supplementary? Do they add up to 180? Yes. Are they a linear pair? No. They are not a linear pair, so that means that would be my counterexample. For here, two angles are congruent, then they are complementary. Congruent just means has the same measure, right? So does that mean that they have to be complementary? Absolutely not. So if two angles are congruent, say I've got a 30-degree angle here and a 30-degree angle here. Are these two the same measure? Yes, they are congruent. They are not complementary. So this would be a counterexample right here. Bam and bam. That means that I have two congruent angles, but they are not complementary because complementary means adds up to 90. 30 and 30 does not add up to 90, so there's my answer. All right, moving on. So if I wanted to look at this and say there are 5,280 feet in a mile. So if I wanted to go conditional, I'll do that in blue. If the distance, because that's what we're talking about, a distance, is 5,280 feet, then it is 1 mile. If I look at the converse, converse means flip it around. If the distance is 1 mile, then it is 5,280 feet. Now I have to consider which ones are true, which one is false, so I can either write it as a definition or find a counterexample. Well, this statement is true, so is this statement. So now I can use that and write a definition. So I can say the distance is 5,280 feet if and only if it is 1 mile. So I use that if and only if to answer my question. All right, that would be my biconditional, and in this case, it would be a definition. Sorry for those, that means that's shorthand for definition. All right, so for your assignment, conditionals, biconditionals, definitions, and then you want to do your review and try and take your quiz sooner rather than later. All right, I look forward to talking to you. Thank you very much.